This is section 2.5, evaluating limits algebraically. First, we discuss what determinate and indeterminate forms are. So these are different from limits and their forms. And then we discuss limit calculation techniques. And we're discussing A, direct substitution, B, simplification, C, conjugation, and D, discrete theorem. And then we're going to discuss limits of piecewise and absolute value functions again. So the form of a limit, limits as x approaches c of whatever, like we put a square in there, is this expression resulting from substitution of x equal to c into that whatever, that expression in front of it, in front of the limit. And so this not always renders a value and a number value. Sometimes, if you've seen this before, we used the infinity and negative infinity before, but also there are indeterminate forms that can result from just substituting in there. And so with the indefinite forms, we definitely cannot write limits of as x approaches c of that expression equal to that indeterminate form. So the form of a limit is not the same as its value. It's a tool for inspecting the limit. And so, for example, limit as x approaches 0 of x to power arc tangent of x is of the form, if you plug in 0 in here and 0 in there, you get 0 to power 0. That's not a number, it's indeterminate form. And so in limits as x approaches infinity of 1 plus x to power 1 over x is of the form, if you plug in infinity in here, 1 over infinity, if that's something that you can do, is going to be 0. It's basically the limit of 1 over x as x approaches infinity is going to be 0, and 1 plus x as x approaches infinity is going to be infinity. So it's infinity to power 0. And that's, again, is not a number, or we don't know whether or not it's 0 or infinity or any number in there. And so the limit is either of them. And so limit as x approaches 0 of cosine of x to power 1 over x is of the form, if you plug in 0, you get 1 to infinity, basically. In here, if you plug in 0, natural log of as x approaches 0 is going to be, from the positive side, is going to be negative infinity, and you multiply by sine, which is 0, and so on and so forth. Determinant forms are forms which always represent the same limit. So if you have a determinant form, you know that the limit is that, even though if it's not a number. For example, the form 1 over infinity always represents a limit which is equal to 0. And because 1 over a denominator that is getting unboundedly big makes the entire fraction 0. Assuming, now, assume c is not equal to 0, c over 0, the form c over 0 is either plus or minus infinity. And form infinity times infinity is always infinity. Infinity plus infinity is infinity. C over plus minus infinity, that form is always 0. Negative infinity times infinity is negative infinity. Negative infinity, form negative infinity minus infinity is negative infinity. So these are determinate form. I know how they, if I get these, I know what the result is. But indeterminate form are called indeterminate because they represent limits which may or may not exist, may be equal to any value. We have to kind of unravel what they are equal to. The form itself does not indicate the value of the limit. There are seven indeterminate forms: 0 over 0, plus and minus infinity over infinity, infinity minus infinity, plus minus 0 times infinity, 1 to power infinity, 0 to power 0, and infinity to power 0. So with the regular in your mind limit type of thing that you do with any of these, you cannot come up with either 0 or infinity or 1, basically. For example, in here, 0 to 0, if 0 to any power should be 0, but any number to 0 should be 1. And so that's why they you can also see from the form itself that you need more clarification to figure out if they don't exist, if they are one of those, or a number, or so on and so forth. So now we can use out of the ways of solving for limits, we can use direct substitution to evaluate limits of functions that are continuous. And that's section 2.4, we saw that in there, or have determinate forms. And so let's say some of this direct substitution may require a little bit of a simplification. So here's the theorem, basically, that or statements that will allow us use simplification to find the limit. And we've seen this before also in the past. So if f of x is equal to g of x for values near x equal to a, then the limit as x approaches a of f of x is equal to limit as x approaches a of g of x. So look at this function to the look at this expression to the left and look at the expression to the right. They are not equal to each other. We cannot just write these two are equal to each other, even though x minus 1 and x minus 1 can simplify from top and bottom, and we end up with that. Why can we not write it like this? Because we haven't specified the domain. And so when you specify the domain, when you say x is not equal to 1, for at least, and so basically you have to exclude the part that makes the left hand side not exist, so you can have the two of them to be equal to each other. If we don't have that x not equal to 1, then in a simple evaluation will tell you that the right hand expression has a value at x equal to 1. The left hand expression does not have a value at 1. So this means that I can do this simplification, but this is an example that I can do this simplification and basically find the limits for this expression everywhere, and so the other thing is that I can exclude x equal to 1 from the domain, but then the shape of the two graphs are basically same everywhere, but at x equal to 1. But I'm finding the limit at x equal to 1. That means that I am looking at the points that are near x equal to 1, and all the points are the same between the two functions f of x and g of x. So I can use this instead to find all the limits for this function f of x. The other method that we use, beside the simplification that we saw, that the two functions are going to be, one function helps the give the limit value for the other function, is the conjugation that we use to basically, from conjugation, we end up with a simplification. And so what is conjugation? If you have an expression a minus b and you multiply it by a plus b, then you will have the difference of the squares as the product. And this basically helps us either, let's say, rationalize the denominator. I can multiply the top and bottom of this numerator and denominator of this fraction by 3 minus square root of 3, and then it would rationalize the denominator. Or sometimes we need to rationalize the numerator, and that's something that comes in handy a lot for in calculus, basically, and we'll see it very soon in this section and the follow-up sections. And so I can rationalize the numerator of this one by multiplying the top and bottom by square root of 12 plus square root of 3. And numerator and denominator, both of them. So both are possible. Now, let's do some simplification and conjugation examples. Let's see. This is limits as x approaches -1 of this polynomial divided by this other polynomial. If you plug in -1 on the top polynomial, you will end up with -2 times -1 to the power 2 plus 4 times -1 plus 6. And that is equal to 0. If you plug in -1 in the bottom part, you're going to end up with, again, a 0. And so this is direct substitution. Direct substitution gives me form 0 over 0. And so that's not, that is going to require some simplification on our behalf. So to solve this limit, what we do is we try to simplify. Why? Because after we figured out the form is 0 over 0, and I see two polynomials, I realize that there is a factor with the root x equal to -1 on the numerator and in the denominator. Therefore, by factoring and simplifying, I will get rid of that, and then I can use the theorem, the statement that we used, by substituting with a simplified form, basically. So in here, I rewrite this limit as x approaches -1, and then I factor -2, end up with x squared minus 2x minus 3 divided by, let's factor this one. This one is, let's say, a 2 and x 1, and this one has to be -2 and plus 1, so they add up to be -1. And so now we also have to do the factoring at top. And so this one is going to be -2 x and 3 and x and 1. Again, this is plus, this is minus, over x minus 2 times x plus 1. So I'm substituting this. If you remember, we said that even though this function is not equal to everywhere to the simplified form, the limits everywhere is going to be the same. And so I'm replacing that in here. So this one is 2. And so at this point, if I direct substitute, what I get is -2 times 4 divided by negative 3. And so this is not an indeterminate form anymore. This was indeterminate form. And this one is not, and I can direct substitute. So direct substitute in here and you get 8 divided by 3. Sorry, it's negative 8 divided by 3. Negative times negative divided by negative 3 times, and it becomes another negative. And so that's the value of this limit. Example 1, part B. If I, again, there's another limit. If I direct substitute, it's going to be square root of 4 minus 2, which is 0, and 0 on the bottom, which is 0. So the form is, again, 0 over 0, and it's indeterminate. So what do we do? Again, it feels like there is a factor that makes the top 0 and a factor that makes the bottom 0. But the top doesn't show any linear factor, but there is a way to find a function with a linear factor, basically bring out that linear factor that makes the numerator 0. Again, over here, when we were looking for the linear factor, we were looking for x plus 1. And over here, because the x minus 1. And here we're going to look for h minus 0. And so we're looking for a linear factor h. And how do we bring that out? Basically, find another function by using the conjugates this time. So I multiply this time. H squared plus 4. H squared plus 4 minus 2 plus 4 minus 2 times the conjugate of that, which is plus, and h squared in the bottom, and if we're multiplying by conjugate, it has to be top and bottom. And then the top becomes just h squared plus 4, which is the first term to power 2, minus the second term to power 2, and over h squared plus 4 plus 2. Now, in this term is going to be h squared. And so there is an h squared in the bottom and h squared on top, and I can simplify that again using that statement. And still, because we're just changing the domain by 0, still we are going to have the same function. Oh, sorry, h squared got simplified. See, here and here. H squared plus 4 plus 2. Now, if I plug in 0, if I do direct substitute, it does not end up with an indeterminate form. So I do that, and the value that we get is 1 over 4, and that's the limit. So this time, example 1, and this is part C, and I try to direct substitute again, and I end up with 9 minus 9 over 0, which is 0 over 0 indeterminate form. What do? I look at this term, the numerator, and I see that may be simplified to something easier. So I'll try use the difference of the square formula. So this is squared, and 9 is 3 to the power 2 Therefore, I go t plus 3 minus 3 times t plus 3 plus 3. That's the numerator divided by t. T goes to 0. And then how I end up is the top is t times t plus 6 divided by t. Another way of doing that was that if you expand the binomial and subtract 9. And these two simplify, and still you will have the same limit even though the domain is changed. And the value of the limit is 6. So the next question is part D of example 1. How do we evaluate this limit? Here, if I plug in direct substitution, I get 1 over 7 minus 1 over 7, 7 minus 7, 0 over 0 again. So I know that I need to figure out a way, and I know the denominator has a linear factor, so I need to figure out a function with a linear factor on top and to be able to simplify with the denominator. So what we do this time is I see that there is a complex numerator going on, so I try to simplify the numerator. First common denominator in here, so it's x times 7 divided by 7x plus 7 divided by 7x over 7 plus x, and that is the limit. X approaches the -7, and it's x plus 7 over 7x over 7 plus x. Remember that 7 plus x is 7 plus x over 1, and so when you can simplify the numerator of that one over the numerator of numerator by the numerator of denominator, and you end up with limit of 1 over 7x. Now plug in limit as x approaches -7. If you plug in, you get -1 over 49, and so the direct substitution works.